Hey everyone, welcome back to some algebra, and we're going to be looking today at section 6.3, which is exponential functions. Now this is kind of one of those subjects which, even the calculus students will have some kind of a trouble really relating to the exponential function, because it's just not something that we see every day. Definitely not something that we would see like the linear function. We usually have a pretty good idea about how that works. And believe it or not, the exponential function is similar to the linear function in that, instead of the mechanism from getting from one point to the other, instead of that being addition, exponential function makes that multiplication. So we have this function here, y equals 16 2 to the x. The fact that we're seeing the x in the exponent here of 2, that's what makes this an exponential function. So here in this exploration, we're going to try to graph this maybe a little bit smarter using Desmos as a tool. So let's get a Desmos window open right now. Okay, so here we have our blank Desmos screen, and I'm just going to type the function exactly as I saw it, but with one exception. After typing y, I'm going to type the number 1, and that's going to give me the subscript y1. That's going to enable me to do a lot of fun things with this graph. So it's equal to 16 parenthesis 2 parenthesis power of x. There we go. Now it's kind of hard to see what's going on here with this function because the graph is, the window isn't very well suited. So let's see if we can, definitely make this taller. We're going to hit the wrench over here, and we're going to adjust the y maximum to be, and just because I know a little bit about the function, I'm going to make this 32. Now, let's make it 50. And that's going to change the look of the window. We can see the graph a little bit more pronounced here. We can see that it actually crosses the x-axis, the y-axis, right there at 16. Now, if only there is a place where there is a 16 in the function. Oh, wait, there is a place. Right over here, there is a 16. Maybe that 16 in the function has something to do with that y-intercept of 16. Now, the next thing I want to do is I want to make a table. So this is kind of like making that chart of values that we saw earlier in our algebra journal. So we're going to literally type the word table in here. And as soon as I hit the E, it's going to turn it into a table. And, I want to turn this into y1. So that's going to help me do this. Let's make this x and y1. So we're going to put a few values here. Let's just do 0, 1, 2, 3, 4. And that enables me to calculate y1 really quickly. And that's why I wanted to call this y1, is that when you call it y1, you're able to use it in a chart like this. So here we go, 16, 32, 64, 128, and 256. Pasting that into my algebra journal, now I can, we look at this graph and I see these arrows pointing down, and I want to figure out, well, how do I get from one value to the next? And, this is the wrong graph. Okay, that's better. How do we get from one graph to the next, or from one line, one value of y to the next? And it looks as though, at least to get from the first number to the second number, I could either add 16 or I can multiply by 2. Two different ways of doing it. How do I get from 32 to 64 now? Well, I could either add 32 or I can multiply by 2. So it's looking like the consistent thing going on with this exponential curve is I'm just multiplying by 2. Let's test that hypothesis out. How do I get from 64 to 128? Well, I could add 64 or multiply by 2. And since multiplying by 2 is the consistent rule that's happening here, that's really the one we should stick with. To get from one row to the next, I need to multiply by 2. So looking at our exponential curve, you can see where that 2 comes from. Multiply by 2, multiply by 2, multiply by 2. Let's move on to question or exploration 2, and we can see the same thing except for we have 1/2 to the x power. So using my hypothesis from up here, instead of multiplying by 2, these should all be multiplied by 1/2. Let's go to Desmos and test that theory. I'm going to change that 2 to a 1/2, and let's see what happens. Okay, notice the graph changes. Now we have a downward trending graph, and as it seems in the graph, so the numbers go. These numbers are decreasing. Copying and pasting that chart over into exploration 2, we can see that the theory worked out really well. To get from 16 to 8, we divide by 2, or we multiply by 1/2. To get from 8 to 4, we divide by 2, or multiply by 1/2, all the way down the line. So now we know what the two numbers here are going to do for our exponential graph. We know that 16, that first number that's not inside the parenthesis, that's going to be the y-intercept. And the 1/2 is going to be the multiply number, kind of like the slope, but with multiplication instead of addition. We're going to learn that that's a number called the ratio. So the number outside of the parentheses, that's going to be the y-intercept. The number inside the parenthesis, that's going to be the ratio. Moving down into the next exploration here that I want to look at, let's take a look at letter A, and we'll compare that with letter B. Letter A, we have 2 to the x. Now notice for this one, there is no actual y-intercept. So if there's no y-intercept, one of the things that is different from a linear curve is that if there's no y-intercept, that means that the y-intercept is 1. So we're going to make a t-chart over here on the left side. We've got 0 and 1 as our first point, kind of like a y-intercept. And then when I increment x from 0 to 1, the rule here would be to multiply by 2, because that's the base of our exponential function. That's going to be our ratio. So 1 times 2 is 2. So we'll just put a point at 1, 2. Increment the x again. Multiply the y-coordinate by 2 again. And that gives us 2, 4. Plot that point. Increment the x. Multiply by 2 again. And that gives us a coordinate 3, 8. Okay, now we just have to fit a line to these points, and there we go. That's our exponential curve. Okay. Setting up for letter B now. Let's zoom in there. All right, that's a little better. Okay, so setting up for B now. This time we do have ourselves a y-intercept, and it is 3 or 2. That means when x is 0, the y-coordinate is going to be 2. And that gives us an opportunity to find our first point on our exponential curve, 0, 2. We'll go to the next point, x equals 1. And we see the ratio now is 3. So now the pattern is to multiply by 3. 2 times 3 is 6. And that gives us our next coordinate, 1, 6. And unfortunately, there's no more room in our graph. So our graph really just is going to contain those 2 points. Now I'm sure we'll have much more graphing of the exponential curves to come. So let's move on to graphing concepts. So here are the points that we were talking about just now. And when b is greater than 1, which means we're going to have growth. So here's that y-intercept that I was talking about, 0a. And then now when b is greater than 1, chances are we're going to see this upward trend. Now, things might change if a is less than 0. We kind of go downward instead. But that's kind of the more rare of the case. The other option here is, what if b is somewhere between 0 and 1? So usually that means a fraction. Fractional value, somewhere between 0 and 1. Well, in that case, we still graph our first point at a, but our trend is going to go downwards instead, toward the x-axis. Here we would call this pattern exponential decay, and we would call this pattern exponential growth. Now that's something that most students won't hear until at least junior year. So if you're hearing it now and you remember it and you understand it, you're probably ahead of the game. So here we go with our extra practice. For this first set, we need to see if this is linear or if this is exponential. So let's see what happens. How do we get from 8 to 4? Well, we have two options. We could subtract 4, or we could divide by 2. And remember, divide by 2 is the same thing as multiply by 1/2. So we're actually going to keep it as multiply by 1/2. How do I get from 4 to 2? Well, I could subtract 2, or I could multiply by 1/2. So we see already that there is consistency here with the multiplication. So this is an exponential function. Let's see. Yeah, let's take a look at number 2 just to contrast this. How do I get from 3 to 7? Well, I could add 4, or I could multiply by, and I think you would multiply by 7 over 3. Okay, that's not a very nice number now, is it? Now, how do I get from 7 to 11? Well, I could add 4, or I could multiply by 11 over 7. Now, I'm sure you can see this pattern here does not work. And the add 4 pattern does work. Or it is more consistent. It's consistent is what I'm saying. So this is a linear function. Okay. Multiplication, exponential. Addition rule, well, that's a linear function. Let's move on to the next set of extra practice. It says to evaluate the function for the given value of x. These aren't terribly difficult, I don't think. You've got y equals 3 to the x and x equals 5. So that gives you an opportunity to substitute 5 for x. So we have y is equal to 3 to the 5th power. And what is 3 to the 5th power? Well, go ahead and grab your calculator. My calculator is Desmos. Let's see, what is 3 to the 5th power? 3 exponent 5, that's 243. Let's do number 7. You've got x is 4, and you have 3 multiplied by 4 to the x power. So y equals 3 parenthesis 4 to the 4th power because of x. Grab your calculator. So 3, 4 to the 4th power, that's 768. Number 8 and 9 say to graph the function and then compare the graph to the graph of the parent function and describe the domain and range. Okay. For question 8, I see a negative 2 to the x power. So be careful here because the negative sign is not part of the exponential part. So this is negative 1 times 2 to the x. We talked about that in past videos as well. Let's take what we learned and try to apply it here. We have a is negative 1. So when x equals 0, y is going to be equal to negative 1. And then if it's 2 as the ratio, then we're going to multiply by 2 to get to the next y value. So when we increment our x to 1, we multiply by 2. And then when we increment our x again, we multiply the y value by 2. And then you just continue. So we're going to set up our coordinate axis next. I can see that my x coordinates are positive and my y coordinates are negative, so that's going to make me focus my graph onto quadrant 4 here. I'm going to try and take up as much of the graph as I can. So I'm going to call this point 1, this one 2, this one 3, and that makes this one 4. And then I'm going to kind of take the opposite approach with the y coordinates. I'll make this negative 2, negative 4, negative 6, negative 8, etc. Then we can graph our coordinates. So the first one is 0, negative 1. I'll have to estimate where that is, but that's okay. 1 and a negative 2, 2 and negative 4, 3 and negative 8, and then 4 and negative 16. And then we just make a line to connect them all. Hopefully this line comes out pretty okay. Yeah, that came out okay. I like that. All right. Let's take a look at our next idea here. We're supposed to graph the function and describe the domain. Oh, that reminds me. Describe the domain and range. We're supposed to do that here as well. So the domain for all these exponential functions is all numbers. So we can write down x is between negative infinity and positive infinity. Now the range, that's a little bit harder to see, but this graph is never going to go above the x-axis. It's always going to stay negative. So our y-coordinates are going to always be between 0 and negative infinity. Or maybe I should write that the other way around. That's better. Negative infinity to 0. So, domain and range. Now over here, we have a parent function and then this minus 2 tacked on at the end here. This means we're going to bring everything down 2 units. So let's graph this one, and we'll start off with a t-chart. And we're going to look at the exponential function, and then we're going to shift it down 2 units. So let's see. We start off with x equals 0. Now there is nothing multiplying to our ratio. So our y-intercept should be 1, but then we're going to subtract 2 from it. Maybe if it's better if we just do the minus 2 at the very end. So right here, instead of graphing y, let's just graph 4 to the x. Okay, because this will make it a little bit easier to see what's actually happening. Okay, so we know that the ratio is 4, so we're going to multiply by 4. 1 times 4 is 4. And then for the next number 2, we know the ratio is 4 again, so we're going to multiply by 4. That gives me, 4 times 4 is 16. And let's do one more. And then we're going to multiply by 4 one last time. That gives me 64. So this is our table of values for 4 to the x. If I want to do 4 to the x minus 2, I'm just going to take each of these values and subtract 2. So 1 minus 2 is negative 1. 4 minus 2 is 2. 16 minus 2 is 14. And then 64 minus 2 is 62. Now we're probably not going to fit this entire thing onto our graph, so don't feel pressured to do it. I'm going to number the axis similar to the way I did in the previous graph, so I'm going to skip a line and put a 1, skip a line and put a 2, skip a line and put a 3, and then a 4. And on this vertical axis, I think I better count by 4. So let's try that. 4, 8, 12, 16. Come to think of it, this is going to fit because I only needed to get to 14. So instead of counting by 4, why don't I count by, I don't know, let's count by 3s. 3, 6, 9, 12, 15. Okay, that's definitely going to fit my data. Now my first coordinate is going to be 0, negative 1. So 0 and negative 1 should be right about here. Because this is going to be negative 3 over here. Next one is 1 and 2. So 1 and 2 right about here. The next one is 2 and 14. 2 and 14 is right about here. And then I'm not going to be able to fit 362. So let's just make our graph now. And I think that's probably the best I can do here. And let's talk next about the domain and range. So the domain here for all exponential functions is negative infinity to positive infinity. And the range, well, this time we have a minimum. So without this minus 2, this minimum would have been 0. But with this minus 2, we're moving the minimum down from negative 2, down from 0 down to 2. So we're basically shifting the entire curve down 2 units. So the minimum here is going to be negative 2 for the y-coordinates, and the y-coordinates won't reach a maximum. So the range is negative 2 to infinity. And then the last one we're going to do here, number 12, we're going to write an exponential function. So we can see that when x equals 0, our y-coordinate is 3. So if we start with the basic, y equals a b to the x power, this looks like my a is going to be equal to 3. To get b, I've got to figure out how do we get from one y-coordinate to the next. So I can already see to get from 3 to 18, we need to multiply by 6. That's not a problem. But to get from 18 to 108, now that's kind of difficult. So, let's check. Does the hypothesis work? Is it multiply by 6? So here on Desmos, we're going to go from where we started, which is 3, and we're going to multiply that by 6 to test our theory. And okay, that got us 18. And then now let's try for the next one. 18 times 6. And yeah, that does give me 108. So it looks like the pattern here is multiply by 6. So multiply by 6. Let's try it one more time just to make sure. What's 108 multiplied by 6? 108 times 6, 648 as predicted. So this tells me that b is going to be 6. So we've got multiplied by 6 to the x power. So that is our exponential function. This was a long one today, people. Sorry about that, but it's kind of difficult to talk about exponential functions without going into a lot of the things that exponential functions are. So we'll see you next time. Have a good one and enjoy your algebra.